Hello, everybody, and welcome back to the Hydrogeology playlist. And insert 100 subscribers celebration here. So, thank y'all. We made it to 100 subscribers. And thank y'all for watching. Appreciate it. So, this is episode 3, and we'll be going over aquifer properties, such as specific yield and retention, hydraulic conductivity, the Darcy's experiment and discharge, and then permeability. And this handsome gentleman on the right is Henry Darcy, and we'll go into his famous experiment that led to Darcy's law. I wish I had his mutton chops, right? Okay, so specific yield, or SY, and specific retention. So specific yield is the ratio of the volume of water that drains from a saturated rock owing to the attraction of gravity to the total volume of the rock. So basically, you have an aquifer that's saturated, and the water that's leaving to, say, another aquifer, or, another aquifer, that would be your specific yield. And so water clings based on surface tension. So we have, the capillary fringe right above the water table, which is right here. You have the capillary fringe, and, particles will have water cling to them through surface tension in the capillary fringe. Gravity pulls the water down. Some will pull away and then drip down to the aquifer. Pendular water is the moisture that clings to soil particles in the unsaturated zone because of surface tension. And at moisture content of specific yield, gravity drainage will cease. So basically, you won't have water leaving the aquifer anymore once it's 100% saturated. And then 2 samples with equivalent porosities, but different average grain size, the surface area of the finer sample will be larger, such as a clay or a silt, in comparison to a gravel or a sand. The clay will have more surface area for water moisture to be held, and that's actually a property of clay, typically. So specific retention it's the opposite of yield. It's the ratio of the volume of water a rock can retain against gravity drainage to the total volume of the rock. And then porosity can be calculated by adding both retention and yield. And then retention increases with the decreasing grain size. So if porosity is equal to 50%, the retention will be 48%. And I like this chart. It kind of shows you that retention is highest in a clay, and in yield, it's at its highest point when you have a coarse sand, medium coarse sand. That means that it allows water to go through. Specific retention is not allowing water to go through, so it makes sense that clay would have the highest retention among all the different sediment sizes that we have down here. And specific yield can be determined in the field. Wells are pumped, and the rate at which water level falls in nearby wells is measured. So basically, the water, as you pump it out, water's exiting from those other wells to bring it to equilibrium, to get the water table back to just a flat level instead of having that cone of depression that's shown right here. It'll start equaling out, and they can measure that. You obviously have to have multiple wells. So one of the most important aspects of hydrogeology is hydraulic conductivity. So pores are connected to some degree, as we talked about in the last episode. And permeability is the ability of a material to transmit water through these pores, and hopefully there's connectivity between these pores. And clay and shell have porosity, but water moves with difficulty due to the small pore spaces. So I like this chart. It kind of shows you the total porosity as the y-axis, and as the x-axis, the volume of shale. So Laminar is basically one or unidirectional flow, and dispersed is basically both types, vertical and horizontal flow. So in a shell, you'll have more porosity as you add more shell content, which makes sense. And yeah, that's basically what that means. And dispersed, you'll have a lot less porosity at this point 3. Well, actually, I don't even know the units, but you know, vertical vertical flow, vertical hydraulic conductivity is much less than horizontal flow in a clay, and that's like I explained in the previous episode. It's because clay layers are deposited as sheets on top of each other, and the pore spaces between each of these sheets is very small, so water has to pretty much travel horizontal, which is why clay makes a fantastic aquitard. So Darcy's experiment. Henry Darcy studied the movement of water through sand beds used for a water filtration, and that's actually an old school way of kind of remediating used water. Send it through sand, and it will kind of help clean up water. And then the rate of the water flow through a bed is proportional to the difference in height of water between the two ends of filter beds, which is the hydraulic heads, and the difference between those two is dH. And then it's inversely proportional to the length of the flow path, and the quantity of flow, which is basically Q, the discharge, is proportional to the coefficient K, hydraulic conductivity, which is dependent on the nature of the porous media meaning soils or rocks, and in this little chart, it's if you've taken a physics class, and specifically a fluid thermodynamic type class, you've probably seen this before. If you took a hydrogeology class, you've seen this before, but it basically shows water flows from high head to low head, and the difference in difference in head over the length between these two pipes, that's going to be your gradient. So the gradient is obviously flowing from here from left to right, because you have high head on this side, low head on this side, and it flows through the sand-filled container and drips out on this side. But yeah, this is just a basic drawing of how Darcy experimented. And discharge, which is Q, is proportional to the difference in height of water, which is the hydraulic head, between the ends, and inversely proportional to the flow length. So if this simplifies it, the symbol means proportional. Q is proportional to the difference between hydraulic head A and B. And Q is inversely proportional to length, the flow length. Flow is proportional to cross-sectional area of the pipe, A, and when combined with proportionality constant, K, which is hydraulic conductivity, you have Darcy's law, which is, you can either do it this way, or the way I know it is, and this is our first calculus formula that we've seen in this channel, it's negative Ka dH over dL, and I'll explain a little of what each of those mean in the next slide. This is another cool visual. A equals the cross-sectional area, K is your hydraulic conductivity, Q is your discharge or flow rate through the aquifer, L is the distance between these two wells, and then your hydraulic head, obviously, like I said, it's going to flow from high to low. So this one's the higher head, this one's the lower head. Flow path is going this way. And like I said, dH over dL, first calculus, because that's a gradient, that's the hydraulic gradient. dH is the change in head, and then dL is the difference in length between those two head points. And then the negative sign, as you saw, the negative sign right here in this formula basically indicates the flow and direction of decreasing hydraulic head, which is how water flows in the subsurface, and typically on the surface too. You have high head over here, flows this way. And then K is a function of the porous media and fluid passing through it. So basically, what type of, are you dealing with silts, sands, clays? That'll affect it. The grain shape and size, that'll affect it. And also, what type of fluid are you dealing with? Are you dealing with crude oil, which moves slower than water due to the viscosity or the resistance to flow? Colder fluids are more viscous than hotter fluids, and K will vary with temperature of water or any other fluid. And then we're getting into permeability of sediments. So unconsolidated coarse grained sediments are the most prolific producers of groundwater. Clays are used to line solid waste disposal sites due to their low intrinsic permeability. Like I was talking about earlier, they are deposited originally in basically sheets on top of each other. So the horizontal, conductivity is not bad. I mean, it's still not great, but it's better than the vertical, which is almost impossible because of the way the clay flakes are deposited, and especially once they become a shell and undergo diagenesis, they're compacted. The pore spaces become even smaller. And then when you're dealing with intrinsic permeability, which is Ki, it's a function of the size of the openings through which fluid moves. Clay has a very low intrinsic permeability because even the horizontal flow, the water is traveling through very, very small pore spaces. And then the smaller the size of the sediment grains, the larger the surface area, which creates a frictional resistance to flow and reduces K. So like I said, clay flake is the smallest, and it's going to have the larger surface area, which will create that frictional resistance to flow and reduce K. So here we have a nice little image showing crystalline igneous rock, which I'll talk about a little bit later, but it has low porosity and low permeability. There's hardly any void spaces. And then here's a clay-rich layer. So you have small pore spaces, basically none vertical, all horizontal, but they're still very small. So you have high porosity, a lot of small pore spaces, but your permeability is very low. And then quartz sandstone, obviously, well sorted. It's going to have high porosity and high permeability. And then glacial till, like we talked about during the porosity episode, it has low porosity and low permeability because you have bigger grains with smaller grains filling the pore spaces between them. So you're lowering your not only horizontal but vertical conductivity. And then another chart kind of shows you the conductivity in millidarcies, which is something more petroleum geology, and then centimeters squared, which is a little more hydrogeology. But as you see, it from well-sorted gravels, you have a decent conductivity, and it goes all the way to -15 on a fresh granite. The crystalline igneous rock is going to have very low hydraulic conductivity. So, for instance, say we have a sand-sized alluvium, indicative of a river stream or something. Several factors relating to the grain size, these 4 factors, hold true for all sedimentary deposits, whether it's a sand-sized alluvium or a lacustrine clay or glacial till. As the median or middle grain size increases, so does the permeability due to the larger pore spaces. Permeability would decrease for a given median diameter as standard deviation of particle size increases. An increase in standard deviation indicates more finer material filling the voids between the larger grains, poorly sorted like a glacial till. And if you guys remember from sedimentology, standard deviation is a statistic that tells you how tightly the data is clustered around the mean or average grain size in this case. And when the sizes are tightly clustered and the distribution curve is steep like the one pictured here in the background, the standard deviation is small. When the sizes are spread apart and the distribution curve is relatively flat, that tells you that there's a relatively large standard deviation. Coarser samples show a decrease in permeability with an increase in standard deviation than the fine samples, because that's glacial till. As you start adding the clays and the silts into, say, a gravel, which would be glacial till, you start having a decrease in permeability. Whereas if you add silts and clays, more silts and clays to a rock such as a siltstone, say you had clays introduced at the same time you're having silts introduced, you're creating a mix of silts and clays. That won't affect the standard deviation as much. And so you have unimodal, or one dominant size, has a greater permeability than bimodal, or two dominant sizes, and that's a result of poor sorting. So like I said, in the it's called the bell curve, and we see that at the introduction of sedimentology. You also see in geotechnical. But when it has a steep curve like this, that basically means that you have a small standard deviation. You have pretty much all your particles are close to the same size. So permeability of rocks. So the size of openings, the degree of interconnection, and the amount of open spaces affects the permeability of rocks. Clastic sedimentary rocks, and this is kind of review if you watch the porosity video. But clastic sedimentary rocks have primary permeability characteristics like unconsolidated sediments, except that diagenic processes can affect porosity. And primary permeability may be due to said structures such as bedding planes or the cross bedding that we saw in the porosity video. Crystalline rocks have low permeability and porosity because the intergrown crystals contain very few openings. Volcanic rocks can have primary porosity, obviously bubbles that form in a basalt when the basalt's cooling at the surface can be primary porosity. And then permeability depends on the connectivity of these pores. Most likely those connectivity, the connectivity would be based on maybe secondary fracturing. Secondary permeability through fracturing increases the permeability initially due to the number and size of fractures, and can increase in size as water moves through them. And then, like we talked about in the last episode, weathering can increase permeability. So in these two images, you have no pore spaces. This is basically what a crystalline, igneous, or metamorphic rock would look like in terms of pore spaces. And then you have these, which may be a highly compacted sandstone, for instance. It has your pores, but you're not, you don't have connectivity. So, it's really a low effective porosity. And then you have your well-sorted sands and gravels or something, and that's going to be porous and permeable. And then, so when you're using intrinsic permeability, you really only use that for unconsolidated sediments, and then use hydraulic conductivity when you're talking about a pure rock. So as you can see, conductivity is highest in a karst limestone, a permeable basalt, a crystalline rock with a lot of fracturing, a carbonate, and a sandstone. And then it's at its lowest in a shale or an unfractured crystalline rock. And we won't go too much in depth on permeameters. I think the book goes more in depth a little bit later on, but we will somewhat cover it. Okay, so they're devices that can be used to measure hydraulic conductivity. And this picture describes a constant head permeameter. And obviously, you measure the time, and you measure the elevation differences as you put water into this device, and you measure the change in water elevation over amount of time. I is basically your gradient, your change in head over the length. Volume is the diameter of the N, which is this tube right here, squared, minus the this squared times pi divided by 4, and then Q is determined by dividing the volume of the device divided by the time, the change in time. And then with that, you can figure out hydraulic conductivity, and that's how they do it in the field. So the next couple episodes, we'll be covering water table, aquifers, important stuff, water table and poniometric surface maps, aquifer characteristics, homogeneity. I have a hard time with that word. Homogeneity, isotropy, gradient of podiometric surface. And I appreciate you guys watching. I'll see y'all next time.